Section 8.3 has to do with trig antiderivatives. And when you're dealing with powers of trig functions, really all techniques here can apply. You might use substitution, you might use integration by parts, you might use some basic trig identities. And we also do have some specific reduction formulas that can be used as well. So is where things can get tricky because there are so many different things that you could try when you approach one of these problems that it can be difficult knowing where to start or where to go next. So for that reason, this is going to be the focus of your lab this week. We're going to use the technology to help us explore these trig antiderivatives. So in addition to the related reduction formulas, I've also given you some relevant trig identities that are useful to keep around. And we're just going to go ahead and jump right into a first example. So this is the kind of integral that we're talking about in this section, a power of a trig function. Now, one word on the notation there, please do remember that when we write cosine cubed of x, what that actually means is we're taking cosine of x, whatever that value is, and we're cubing that value, not just the x, but the actual cosine of x. So cosine cubed of x is the same as taking cosine of x times cosine of x times cosine of x. The only reason that we put the cubed here instead of at the end is again to avoid that confusion about whether we're cubing only x or whether we're cubing the cosine of x. So when you're given something like this example, the integral for cosine cubed x dx, we do have reduction formulas, and I'm going to go straight to that because this is a fairly simple one in the sense of we don't have multiple trig functions, we only have cosine. You can see in this box we have a formula for any power of cosine so long as that power does not equal 0. And to use this reduction formula, you would just go through and in every case where you see an n, we're going to substitute our n value, which is 3. So here's what that would look like. The only thing I've done at this point is literally just to substitute 3 for the n's. So you can see I've got a lot of calculations now that I can simplify. Now that I've simplified, I look and I see I do still have an integral remaining. Remember, we can use reduction formulas multiple times if we have a particularly large exponent. In this case, though, we've already gotten down to an integral that we can evaluate with just normal techniques. So that would be the next step, is to evaluate the integral cosine of x. And we're done. In the next example, we're confronted with powers of multiple trig functions. So a simple reduction formula, such as one of these, is not going to apply in this situation. So we need to start thinking of some of the other techniques that we've seen. When you have trig functions and they are derivatives of each other, substitution usually comes to mind. Because if I was to let my u be cosine of x, for instance, my du would be negative sine of x. And in terms of matching the original integral, both of those show up. So this seems like it might be viable. I do need to worry about these exponents, of course. Or maybe I let my u be sine of x, in which case my du would be cosine of x. So the point here is that substitution, when you're thinking about, should I try substitution here, you want to think about what one of your functions is and what its derivative is going to be and whether or not those show up. So substitution does seem to play a role here. However, if I was just to work off of, I'll use sine just because the negative is not there. If I were to say, okay, this is my substitution, and I were to try to write my integral off of that, I have cosine cubed x. Now here, I only have cosine of x, so they don't quite match. So I run into a problem as soon as I start. So in some way, we need to work with these exponents before we're going to be ready to do our u substitution. Well, there's a trig identity that also relates sine and cosine. So this is where, again, you kind of pull out all the tools that seem to have some connection. Sine squared plus cosine squared equals 1. If I were to solve, let's say, for cosine squared, when I look at my integral, I have cosine cubed. Cosine cubed is the same as cosine squared times another cosine. So if I were to rewrite this cosine in terms of sine squared, that would eliminate this from the integral, and I'd only have one cosine left, which can be found in my du. So I'm going to go over here. I'm going to solve this identity for cosine squared. So I'm going to subtract sine squared of x on both sides, leaving me with cosine squared of x equals 1 minus sine squared of x. I'm going to use the fact that I can split cosine cubed into cosine squared times cosine of x, and I still do have that sine to the fourth power here. But now I'm going to replace this cosine squared with what it's equal to. Now, it may not seem like that's a step in the right direction until you go back and consider the u and the du that we thought of in the first place. If I let u be sine, let's see where that leaves me. I would have 1 minus, since this is sine squared of x, this would be u squared. The cosine x dx is the same as du. So I'm going to have a du out here. And then the sine to the fourth power of x, that's just u to the fourth power. And so notice what happens is I have a very doable u integral as a result. So the key was to realize two facts. Number one, that sine and cosine are derivatives of each other, and that there's an identity that will allow us to switch one into the other. Using both of those tools, we have this integral. And just by distributing the u to the fourth to both parts, I have the integral of u to the fourth minus u to the sixth du, which of course is going to be u to the fifth over 5 minus u to the seventh over 7 plus a constant. And now I substitute my original u back in. Done. Now I want to step aside and take a look at this in Mathematica, because even though I've got an answer, how do I know that I'm right? So we're going to use technology to confirm this. For the benefit of those of you using the web-based version of Mathematica, I'm going to use text-based commands, but certainly the formatting is easier if you do have the basic math assistant. I'm going to go ahead and put in my integrate command, and I'm going to put in the original integral I was given. Now, to type in powers of trig functions, it's a little complicated. I'm going to open up parentheses, type in capital COS with my square brackets, close, and you do have to put the exponent on the outside like we talked about earlier. So that's the way to represent cosine cubed of x. Now I want to take that whole quantity and multiply it by capital SIN sine of x, close, exponent, close. So there's my trig function I want to integrate. I put a comma x for my variable and do shift enter. Now, if you notice, what I get here does not look anything like what I got when I did the integration by hand. And so I'm left with the question, did I do something wrong? Did Mathematica do something wrong? Did I type it in wrong? So to help us figure that out, we can use the trig reduce command. If I type in trig reduce, open up square brackets, and I just copy and paste my last output into those square brackets, do a shift enter, it's going to just combine that trig expression into a single fraction. Now, I thought the answer was supposed to be the sine to the 5th x over 5 minus sine to the 7th x over 7. So I'm going to go ahead and type that expression inside the trig reduce function. So this is how my trig reduce statement would look. And it may seem like I went a little bit crazy with parentheses here, but especially when you're using text-based commands, it's better to have too many than too little. So I'm going to go ahead and do the shift enter on this. And now you can see we can compare these two expressions and they are in fact equivalent. So this confirms for me that my answer was correct. This is where you have to be careful because if you use Mathematica, you may get one answer and it may resemble nothing like the answer in the back of a textbook, for instance. So trig reduce is one way to confirm whether or not you integrated properly. Another way that you can accomplish the same thing is to look at the graphs of the two statements that you're wondering if they're equivalent. So I can do the plot command. And again, I'm going to take the output of the integration done by Mathematica, and I have to put in my specified x values. Now, since this is a trig function, I'm going to go with a fairly standard interval of -2 pi to 2 pi, and pi must be capitalized. I ask Mathematica to plot that. So that's what it says the integral should look like. So now I'm going to go ahead and take my answer. And again, I can do this just by cutting and pasting. And I'm going to, again, give the same interval. And I do get the same graph as well. So these are both ways that you can confirm whether or not you're getting the right answers to complicated trig problems. Here's another example. In this example, I've got secant and tangent, so I want to think about what I know about the relationship between secant and tangent might be. Again, I would consider probably use substitution first. So I want to think about, okay, what was the derivative of secant? And you may not remember, but certainly you should be able to look it up, that it's the secant of x times the tangent of x. So once again, it seems like this could be relevant because just by letting u be secant, we introduce a tangent, which is part of our integral. Or maybe I want to think about letting my u be tangent, and the derivative of tangent is secant squared of x. So here are some substitutions that do seem like they're going to be relevant. I also, though, should always, again, consider all my tools. So going back to the helpful trig identities I gave you, there's this one. Tangent squared of x plus 1 equals secant squared of x. So I'm going to bring that into the mix as well. And I'm just going to go ahead and kind of commit to one of these two, see what happens. And again, as always, if it doesn't seem to be leading me in a good direction, then I'm going to go back and I'm going to reevaluate. So I have a secant of x, I have a secant of x tangent of x, and I've got cubes on both of these here. So I'm going to consider maybe if I just break up the secant into a secant squared of x times the secant of x, kind of like we saw in the last example with the cosine. And then I've got a tangent cubed x dx. Secant squared x equals tangent squared of x plus 1. Then I have secant of x, and then I have tangent cubed of x. And since I introduced tangent, I would probably want to try this u substitution where I let tangent be my u. So let's see what happens. I get the integral of u squared plus 1. Now here's where I feel, I only have one secant, and my du is a secant squared. So maybe that's not the right way to go. So I'm going to go back. Maybe instead of splitting up the secant cubed, I should split up the tangent cubed. So here I have pulled a tangent squared out, and I'm going to want to go to my identity then and solve for tangent squared so that I have a nice way to substitute and get rid of that tangent squared. And I'm going to bring that back over into my integral. So I'm going to have secant cubed x. Tangent squared x, I'm now going to replace with secant squared x minus 1 times tangent of x dx. And since I introduced more secants this time, it would be more logical to choose the u substitution where secant is my u. So again, I'll just see how this goes. Secant cubed of x would be u cubed. Secant squared of x minus 1 would be u squared minus 1, and then, I have tangent of x dx, which does match part of my du, but it doesn't match the whole thing. So the last stroke of genius with this one is to realize, I have an extra secant over here that I could borrow from. So I'm going to take secant cubed, write it as secant squared x, and a secant of x. I keep the rest of the integral the same. And now what that allows me to do is my secant tangent shows up. Secant tangent dx. So all these blue parts are going to be my du. Now I've got u squared times u squared minus 1. I have my du, and finally, this is a workable u substitution. And again, I've tried to show you kind of just going forward and trying stuff and making mistakes and having to go back, because that's what this is like. There's just no getting around that. So to finish, I'm again going to just distribute, integrate, and finish by putting your u substitution back. And there's my answer. Now let's go check Mathematica and see if it agrees with me. I'm going to type in integrate and the original problem that I was given. And in this case, you should be able to recognize that this is directly equivalent to the answer that I came up with. So in this case, I'm feeling pretty confident here. But you still could apply the trig reduce command to the result that Mathematica came up with for the integral. It will write it in another way. And then I can use the trig reduce command on my answer, which is similar again to what Mathematica had, but just a little bit different. And you can see it reduces to the exact same expression as before. So in this way, you can kind of use the technology to help you to check your homework. But again, just realize that when you do integration, it is common for you to get one answer and then you to check somewhere else and it looks like it's a different answer, but they might just be equivalent forms.